Here's the question in Newton first law as well. Um, this question, guys, it says a box of mass of 7.5 kg lies on a rough surface inclined at 23 degrees to the horizontal. The box is stationary and inclined as shown in the diagram below. Guys, once an object is stationary or it's at rest or it's moving at constant velocity, you must know it's Newton's first law. This is object, it's at an incline. Now the question 3.1, it says define the term static frictional force. Static frictional force in a nutshell, guys, it's the force, it's the frictional force of an object that is not moving, basically. But according to the exam guideline, the way you're supposed to define it, it says static frictional force is the force that opposes the tendency of the motion of a stationary object relative to the surface. Right? Now 3.2, it says draw a label free body diagram indicating all the forces acting on the box while it's stationary. Guys, I'd like you to do the force diagram to show in the diagram what are the forces that are acting there before we do the free body diagram. Guys, when an object is lying on the surface, there's a force that the surface acts on it. It's a normal force, and a normal force acts perpendicular to the surface, right? That is a normal force. Do you see it's perpendicular? It makes 90. And there's a force, there's a gravitational force that acts on an object. And this gravitational force, it has components. It has an FG, perpendicular. It has what? An FG parallel. And FG parallel, guys, it's always going down the slope. It's always going this way of the slope. And the FG perpendicular, it's equal to the normal force. It opposes the normal force all the time, right? And then now, since the object is stationary, it has a static frictional force that is going where upwards. There's a static frictional force, it's called Fs. It's static because it's not moving. That's the force that keeps an object from not moving. So drawing the free body diagram now in 3.2, guys, since the surface it's on an incline, you can make the broken line of an incline representing that incline, and represent the 75 kg box by a dot and a normal force, FG perpendicular and FG parallel, and Fs. There are two ways you can represent that. The one that I've done, guys, is the free body diagram using the components of the FG parallel of the gravitational force, or I can do it this way. I have the normal force, I have the FG, and the Fs. Those are the two ways that I can do the free body diagram, guys. Two ways. You get the marks for both, but the one that helps you in this, it's this one. The one that has components, it's really assisting. Now let's go to 3.3. 3.3, it says calculate the magnitude of the static frictional force. The magnitude of the static frictional force, guys, here, since an object, okay, let's write here 3.3.1. Since an object is not moving and it's stationary, that means the frictional, the F net, the acceleration is 0, and therefore the F net is 0. So you say F net is equal to ma, right? And then we say F net is equal to 0 because the acceleration is 0, right? Because the acceleration is 0. And then the forces that are acting parallel to the surface, or the forces that are involved in the movement, is those two. And then I choose down the slope is positive. So FG parallel is going to be positive minus the FS, right? The Fs, which is the static frictional force, equal to 0. So FG parallel is equal to the static frictional force. So in this case, now we are asked to find the static frictional force. So the way we're going to find the static frictional force here, we will have to calculate the FG parallel. So the static frictional force is equal to the FG parallel. FG parallel is going to be mg sine theta. So which is our mass here. The mass is 75 kg times 9.8 sine, what is an angle? It's 23. It's 23. So 75 times 9.8 sine 23 degrees. It's the answer here. It's 287.19 newtons. Right, I don't know what I've written here. It's sine 23 degrees. So that's the static frictional force, right? Remember guys, here the static frictional force and the FG parallel are equivalent because the object is stationary. So these two forces are equivalent. These two forces are equivalent because an object is stationary. Now at 3.3.2, it says calculate the coefficient of static frictional force, coefficient of static friction between the rough surface and the box. So we want mu k there, the coefficient of kinetic friction. The mu k, it's the description of the surface. It describes how rough or how smooth the surface is. So the way we're going to calculate, we use the formula that says Fs is equal to mu k, not mu k, it's mu s times normal force. Normal force. But now what do you need to understand? The normal force now, it's equivalent to the FG parallel. Normal force is equivalent to the FG parallel because the F net vertically it's 0, so that makes these two equivalent. Right, so we're going to have mu s times FG perpendicular. So what we're going to have, mu s times the FG perpendicular, it's mg cos theta. Guys, you don't have to write the two, you can write any of these, not all of them. So the frictional force, we do have it, it's 287.19, and then the mu s is the one that we're looking for, and the mass, it's 75 times 9.8 cos 23 degrees, and then we'll divide by 75 times 9.8 cos 23 degrees. Even in this side, 75 times 9.8 cos 23 degrees, and then our mu s is going to be, when you punch that in the calculator, so you'll say 287.19 divide by 75 times 9.8 times cos 23. So our mu s, it's 0.42. The mu s, guys, it's a ratio between forces. It has no units. So the ratio between forces, it has no units. So you leave it like that. Now this question, it says now the rough surface is now tilted at an angle 18 degrees to the horizontal. So the rough surface is tilted, which is the rough surface now that it has been decreased, the angle now. The angle has been decreased. So it says now, to the horizontal, how will the magnitude of static frictional force compared to the value calculated in 3.2.1 choose greater or equal to? Guys, I'd like to prove this by calculation first, and then we'll conquer 3.4. So they wanted the Fs. How will the Fs be affected when we don't know why I'm writing this formula again. So now we'll take this value and we substitute. We'll have 0.42 times 10 to the power. What is the mass? The mass is 75 times 9.8 cos. Now, since we know the frictional force, the initial frictional force, this is the Fs is equal to 287.19 newtons at what? At 23 degrees. Now we wanted the Fs. What will be the Fs at 18 degrees when we decrease the angle? When we tilt it, we decrease the angle to what? 18 degrees. So I'm going to substitute 18 degrees there. So in my calculator where I was calculating, I'll just remove 23 and put the 18. No. Okay, I'll say 0.42 times 75 times 9.8 times cos 18. Cos 18. So at 18 degrees, 293, it's going to 293.59 newtons. Do you see the static frictional force is becoming greater now? What causes that? The answer here is what? It's greater. It's greater. So what do you need to notice? Now if they ask you what do you need to notice when it was 23, look at your FG perpendicular. Your FG perpendicular was 75 times 9.8 cos 23. Your FG perpendicular, not parallel, your FG perpendicular, it was 676.57 at what? At a 23. Now let's look at the FG perpendicular at 18. What is FG perpendicular at 18? At 18, the FG perpendicular has increased to 6,99.02 newtons. So this is because your FG perpendicular increases, right? So if your FG perpendicular increases, okay, let me put it like this. When the angle decreases, which is from 23 to 18, your FG perpendicular increases, and therefore your FS increases as well, because your FS is directly proportional to your FG perpendicular. That will be the